Alright, hello everyone. Welcome to another episode of Rainy Science. Second episode, hell yeah. I'm going to talk about electrons today. I'm going to talk about the Bohr model of electrons. If you're new to chemistry, you need to learn this. If you're looking for the quantum model of electrons in the atom, I'll make that video eventually. But if you are new to electrons or don't know the Bohr model, it is essential to learn this first. So let's ripple. I want to talk about the history of atomic models very quickly. I know it sounds boring, but it really helps me with understanding, and I believe it helps people with understanding as well. So we've had different ideas about atoms over the years. Obviously, the more research experiments, the better technology gets. We get much better at finding the truer version of what the atom is. So Thomson believed that there was a positive sphere, that was the atom, and the electrons, the negative charge, was embedded in that sphere, kind of like the plums in a plum pudding. And then Rutherford disconnected these two things, said there was a center of positive charge surrounded by some whizzing electrons, some negative charge whizzing around willy-nilly. Bohr advanced on this idea by to explain some of the experiments, some quantization, some light-absorbing properties of electrons, which we'll get into. Bohr stated that the electrons orbit the center, the positive center, in these orbits. So these specific distances from the nucleus, whereas Rutherford, they were sort of just willy-nilly everywhere. And in the quantum model, which is our most up-to-date, most recent, most accurate at predictions, chemical reactions, etc., the electrons still orbit, but not like Bohr said, like planetary orbits. It's not really like that. Electrons are at specific distances from the nucleus, but they occupy these weird shapes, these weird spaces, which it's if you don't know the Bohr model first, it's so much easier. That's why we're going to focus on the Bohr model today, to then interpret and understand further the quantum model. And yeah, like I said, there are similarities between these two models. You have the center, the nucleus, with the protons and the neutrons, and then the electrons are surrounding the nucleus. However, the spaces they occupy are different. It's more up-to-date in the quantum model, but as you can see, and it gets way more confusing than this, you get some like donut shapes and stuff. But the important distinction with these models in particular is that the electrons are found in specific spaces around the nucleus and are not just sort of circling it willy-nilly. So without further ado, let's move on to this amazing slide that I made. I'm very proud of it. So this is a carbon atom. We talked about atoms in the last episode. So you have the center with the protons and the neutrons. Carbon has 6. Well, a carbon atom has 6 protons, 6 electrons. You can see these 6 electrons here, 1, 2, 3, 4, 5, 6, and they are orbiting the nucleus at these specific distances. So the first and closest orbit distance is, 1. We just label these chronologically. So 1, 2, 3, 4, 5, etc. And this n equals 1, n equals 2, and will be used a lot in chemistry, especially when we're talking about orbitals. It's the principal quantum number, that's the term for it. It represents orbits, distances from the nucleus where electrons occupy. And not only are these just specific distances or specific orbits around the nucleus, they also have a specific energy. Which isn't as important until the next episode where we talk about light and quantization. But what's important to understand here is that electrons occupy these orbits and they are chronological. So 1, 2, 3, etc. Quite easy to remember. And that we identify these just as n. In the quantum model, we would probably say something like n equals 1 is the first energy level for the electrons to occupy. Now, as we can see here, there's 6 electrons for carbon, and n equals 1 only has 2. While n equals 2 has 4, the rest of them. So I'll explain why that is. With the Bohr model, it was established through experiments and calculations, all that kind of jazz, that the first orbital, n equals 1, for any atom can only hold a maximum of 2 electrons. So you will not have more than 2 electrons at this distance from the nucleus. However, n equals 2, the next distance away, the next orbit, can hold a maximum of 8. With carbon, we only have another 4 to fill, so this second orbit could hold more electrons and does hold more electrons for atoms with higher number of protons and therefore electrons, or ions in chemical reactions that accept new electrons. So the first orbit can only hold 2, n equals 1 can only hold 2, n equals 2, the next orbit can hold 8, and this is true for any atom when you are drawing one of these diagrams. And then n equals 3, which of course has no electrons here because we haven't filled up the second orbit yet with 8. So before the third one could start filling with electrons, before the electrons would start orbiting at this distance, this second orbit would first have to fill with 8 electrons. However, confusingly, the n equals 3, or the third orbit, can hold a maximum. It depends on who's teaching, what textbook you're reading. Some textbooks say 8 maximum electrons for the third orbit. Some say 18. I will explain in this video very lightly, but I will show on the periodic table sort of why that happens. Now, the good thing is you do sort of move on to the quantum level of electrons and orbits before playing with atoms that would have this amount of electrons. And when we're using the Bohr model, when we begin our chemistry education, we only really associate and talk about atoms and draw out atoms that use the first 2 orbits. Of course, there's probably a trick question in an exam that will have you fill out some of the third orbits. They are the transition metals and some of the more heavier atoms. So usually we only play with these 2 orbits. So it depending on who's teaching, 8 or 18, just make sure in an exam that you are doing what is expected of you relative to that syllabus. But just remember 2, 8, 8 or 18. 2, 8, 8 or 18. So with oxygen, for example, just switch to oxygen. This oxygen has 8 protons, the oxygen atom, and therefore it's neutral, so it has 8 electrons. The extra 2 electrons have filled out or come into this second orbit. You can see here that the n equals 1 orbit remains the same for both. Oops, switch to neon. So it always fills with the 2 there first and then moves on to the second orbit. So you've got 1, 2, and then 6 in n equals 2. So it's still not full. N equals 2 can still hold another 2 electrons before this third distance, this third orbit, will start to fill up. And oh my god, I have that right here with neon, one of the noble gases. So we have our n equals 1 holding the 2 electrons. So neon, has 10 protons, 10 electrons, the neutral atom of neon. The second shell, the second orbit, has now filled up with 8 electrons, so there's 10 in total here. Any extra electrons, whether neon becomes a negative ion if it accepts more electrons, or if we move up to sodium, which has 11 electrons in the neutral atom, will then start to fill in this third orbital. Because n equals 2, the second, is full. It has 8 electrons. So switching between neon and sodium, you can see that this additional electron is starting to fill in the third orbit. So the takeaway from these slides in particular is that we fill up chronologically, so from the closest orbit to the furthest orbit. So we have 11 electrons for sodium. The first 2 will go in n equals 1. The next 8 will go in the second orbit, and once that fills up, n equals 3 starts to fill up. And the 8 or 18 is confusing, I know, and it's annoying, but that happens a lot in chemistry. It does get explained later. Believe me, it's just easier to sort of accept some of these things. So once again, the n equals 1 orbit is the closest orbit to the nucleus and fills up with a maximum of 2 electrons. N equals 2 is the next orbit away. Because hydrogen and helium don't have enough electrons to fill up, to start filling up the n equals 2, we only really look at the n equals 1. However, we talk about later that electrons can move between these orbits. So it's important to also understand that even though n equals 2 or n equals 3 or any of the orbits aren't visible here for hydrogen and helium, that they still exist. So we don't have to draw them, obviously. We'd be here forever drawing concentric circles, but just understanding that it's only really necessary when an electron is in it. Now, what's really important to understand and know is valence shells or valence electrons. What we're talking about with valence shells or valence orbits, shells is more used in quantum, but they are synonymous, shells, orbits, but the valence shell or valence orbit, it's the orbit that is the furthest away from the nucleus, that has at least 1 electron. So for example, with sodium, the third orbit is the valence orbit or the valence shell, and therefore this 1 electron in sodium up in the third orbit all the way, he is the valence electron. Whereas with lithium and neon, the second orbit is the valence orbit, the valence shell, and therefore these are the valence electrons. So if someone asked you how many electrons does neon have in its valence shell, you'd go, okay, well the valence shell is the second one because the third one doesn't have any electrons in it, and it has 8 in there because neon has 10 electrons, so 2 in the first, 8 in the next. With lithium, the second orbit, n equals 2, is the valence shell, the valence orbit. And this, it has 1 electron in its valence shell. So it has 1 valence electron. And hydrogen and helium, n equals 1. There's so many colors happening. N equals 1 is their valence shell, and hydrogen has 1 valence electron, helium has 2, lithium has 1, neon has 8, sodium has 1 valence electron. Now, the reason that it's important to understand valence shells, valence electrons, these are the electrons, the valence electrons are the ones that do all the chemical bonding. They participate in the reactions, because if you have another atom coming in next to another one, the valence electrons, the ones furthest away from the nucleus, are going to interact first with the other atom. So for sodium, for example, you have these 3 shells, these 3 orbits, n equals 1, 2, and 3. However, the first 2 are filled. They have their maximum amount of electrons, and they're also closer to the nucleus. This 1 electron out here is going to be the first one to participate in a reaction. Also, the reason that they have these maximum electrons, that's when you hit the maximum, the orbit is happy. So that's a weird concept, but equations and all that kind of stuff, it would rather hold on to or achieve the maximum amount, or not have any in it at all in the orbit. So let me just extrapolate on that a little bit, because that was a confusing way to put it. But sodium has 1 electron in its valence shell, in its valence orbit. It has 1 valence electron, and an atom would either rather have its orbit completely filled or have nothing in it at all. Just energy-wise, it's better. The universe works in mysterious ways to distribute energy, and this is one of them. So sodium, you might have heard of sodium chloride. It's table salt. So chloride takes this 1 electron from sodium, and sodium gives it willingly. It's happy to release this 1 electron, because then it will have its perfectly filled shells. And this one, which can hold 8 or 18, isn't filled yet, and it's easier to release this 1 electron and have an empty orbit versus trying to fill it up with a lot of other electrons. So in chemical reactions, you'll find that sodium always forms a positive ion. It always would rather give away this 1 electron. This is getting a bit into chemical bonding, and we'll get there, but I do think it's important to understand now as well. However, oxygen, I don't know why I didn't put oxygen on the other screen. Oxygen, so n equals 2, it has 6 electrons in here. It can hold a maximum of 8, and it's easier to get, it's easier for oxygen to grab 2 electrons than release or give away 6. So in reactions, oxygen likes to form a -2 ion, which means that it has 2 additional electrons that will fill this n equals 2 shell, and then it's happy. So it does explain chemical bonding and chemical reactions as well. So this is the valence shell for oxygen. This third one has no electrons in it. It's not a valence shell. I'm going to go through the first few elements of the periodic table. So hydrogen has 1 proton in the neutral atom, therefore 1 electron, and that starts to fill the first n equals 1 orbit, which can hold a maximum of 2, which helium has 2 protons and therefore 2 electrons in the neutral atom. So this second electron goes into the n equals 1 orbit. However, when we start moving up to atoms with more electrons, they'll start filling up the n equals 2 before they move on to the n equals 3, etc. So what I've done here is all of these still have their n equals 1. I've just graded out, and they do have their first 2 electrons in the n equals 1 shell or orbit. So lithium is the third atom on the periodic table. It has 3 protons, therefore 3 electrons, and this third electron begins filling the n equals 2. So this is now the valence shell. For all of these that we're looking at here, n equals 2 is the valence shell. For hydrogen and helium, n equals 1 is the valence shell, and therefore these are the valence electrons. So as you can see here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. This is elements 3, 4, 5, 6, etc., all the way to 10. And we are filling the n equals 2 shell up until neon hits 8. Anything above this, which I have made, we'll start filling the n equals 3. So once again, so this is sodium with 11 electrons, 11 protons, 11 electrons. The first 2 in n equals 1, the next 8 in n equals 2. and now there's additional in the n equals 3, and this is now the valence shell. It has 1 valence electron, and what's really cool about that, well, I think it's cool, and I'll talk more on this in the periodic table episode, but if you see these numbers here, 1, 2, 3, 4, 5, these rows of the periodic table, hydrogen and helium are in 1, n equals 1. Lithium, beryllium, all the way to neon in 2, n equals 2. And then sodium begins filling up the n equals 3. And I hope you can see this. This is really cool, I think. But see the massive hydrogen square here? See how it's got a 1 in the top right? And I move to helium, now it's got a 2. Move to lithium, it's now 2, 1. So that is the amount of electrons in n equals 1. And now n equals 2 is starting to fill up. So as we move to beryllium, we'll see that that goes to a 2. Another electron goes into n equals 2, etc., all the way up to neon. Now we have 2, 8, sodium, 2, 8, 1. The third is now being filled. This is a great way to quickly see which is the valence shell. So for lithium, beryllium, all the way to neon, the second is the valence shell. For sodium to argon, including chlorine, sulfur, phosphorus, etc., the third shell, the third orbit, the third distance is the valence, and therefore, so this has 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons in n equals 3. And I'm sorry if that's a bit confusing or a bit out of scope, but there are some incredible connections between all of these things that I think if you understand, it retains the knowledge a lot better, for me in particular, and I always enjoyed this kind of stuff. But the periodic table's incredible how well it's organized. So because these took a painstaking amount of time to make, I just did the first 2 of n equals 3, sodium, magnesium. You can see n equals 3 is filling up, and then the ... represents all of the other ones up until argon, which is a noble gas. And has 8 electrons in its valence shell. Something about noble gases, this is also important actually. So these guys here in column 18, the noble gases, and so before I was saying that n equals 1 always fills with a maximum of 2 electrons, and it would like to be filled with 2 or none. N equals 2, the next orbit, fills with 8. It would rather have 8 electrons or none. It will always, atoms prefer to participate in reactions that will fill or have empty those shells. Just for energy reasons, neon, 2 and then 8. So the n equals 1 is maxed out, the n equals 2 is maxed out. Neon is a noble gas, and the noble gases don't really participate in reactions too willingly. They're quite happy and stable energetically. And that is because of this filling of the orbits. Sodium, which then adds an electron to the n equals 3, would rather have this configuration of the 2, 8. So it participates in reactions where it will give away this 1 electron in the n equals 3. So it will happily react with chlorine. Well, this is going to be tricky. I want to keep chlorine up. And the reason why, god damn it, is because, so if you just look over, chlorine has n equals 1 has 2, n equals 2 has 8 electrons, n equals 3 has 7. It would like to add an electron. It's much easier to add an electron to fill up that n equals 3. So you can think about it that these atoms would like to participate in reactions to reach a noble gas configuration. So sodium will willingly give up this 1 willy-nilly electron to reach a more stable configuration of electrons, and chlorine will happily take that 1 electron because then it will reach the 2, 8, 8 stable configuration. Remembering that n equals 3 isn't always 8 as the maximum. N equals 1 and n equals 2, always 2 and 8. So much more important to remember that it goes 2, 8, and the third one has a little bit of an asterisk, 8 or 18. So the reason n equals 3 and above is so weird is because of the quantum model, and the distances between these orbits and stuff. It gets a little bit funky. So just to anchor us, remember hydrogen, n equals 1, helium, n equals 1, they're filling up. And then this second row, the n equals 2 is filling up with electrons. And then the n equals 3 starts filling up with electrons. Once we get from argon to potassium, you'll notice n equals 4 starts filling up instead of n equals 3 reaching 18. However, if we scroll across, it gets a little bit more confusing because n equals 3 sort of takes some electrons once n equals 4 has some electrons, and it sort of just flip-flops a bit. But when you do reach, it looks like, yeah, copper, it does have 18, and then we focus on n equals 4 filling up. and I believe that can fill up to 18 or 32. Yeah, it just gets a bit confusing. But you'll notice that it's always 2 and 8 in the first two. That's very solid. And then 8 or 18. And then 8, 18 or 32. But we really don't play too much with these atoms until we get to specific areas of chemistry, transition metals, stuff like that. And depending on where you're learning, they might say in an exam that you should fill n equals 3 with 18 before filling n equals 4. Or some may say that you fill n equals 3 with 8 and then move on to n equals 4. I know it's a little bit annoying, especially I found it annoying because you just want to have an answer, a way to figure out the electron configurations for things, and you want to know the right answer. However, it's complicated. The universe is complicated. But yeah, I hope that sort of gives some context. With these guys, you're always pretty solid. You've got the 2 in the first one, 8 in the next one, and then you can start filling up to 8 for n equals 3. That is correct. However, after that, it does start to get a little bit confusing. So I'll just move on. Oh yeah. I put this button here just to demonstrate, once again, the valence shells. You have to be able to identify the valence orbit or shell, and therefore the electrons within that orbit or shell are the valence electrons. They are the electrons that will participate in reactions, and depending on whether it's more favorable for an atom to lose or gain an electron to fill the valence shell or empty it, that determines chemical reactivity, which we get into later. The noble gases have stable configurations, that is, it's more energetically favorable to just exist on their own and not really participate in the swapping of electrons in chemical reactions. They're pretty happy as they are. And it is confusing, once again, because argon, a noble gas, has 8 and n equals 3, but krypton has 18. So yeah, once again, annoying. But the valence shells here, n equals 1, n equals 2, n equals 3 are the valence shells. The amount of valence electrons depends on the atom. For sodium it has 1, for magnesium it has 2, and magnesium always sort of forms a +2 ion in reactions. That is, that it will give away these 2 electrons to form a +2 ion in a ionic bond. But I will expand on that in a periodic table video. I think I've gone way out of scope for this, but that's okay, that's very me. So yeah, in the next episode I'll talk about light and quantization, and I did want to put it in this episode because the Bohr model, the groundbreaking difference of the Bohr model is that these are specific distances from the nucleus, these orbits, and therefore the electrons within them have a specific amount of energy and can absorb or emit light, which is energy, to change their orbit. They can skip to another orbit or drop down to another orbit, never in between. So that's what quantization sort of means. These are quantized orbits. They have discrete energies, discrete distances from the nucleus. I hope that made sense. And yeah, those are the takeaways of the Bohr model. And yeah, it is extremely important to then understanding the quantum model, which we do get into later, and is very cool. I do love the quantum stuff. But the most important thing is to understand that n equals 1, n equals 2, n equals 3. It's the chronological numbering in terms of distance away from the nucleus, and that orbits can hold specific numbers of electrons, and chemical reactions happen because they would rather give away or receive electrons to fill or empty these orbits, whatever's energetically favorable. Just understanding these things gives us some idea about chemical reactivity, and yeah, what ions the atom might form. So yeah, thank you so much. Have a good one. Bye.